One thing about pretty much everything in life, including electronics, I've discovered, is that as time goes on, the things you already understand, you begin to understand better. You keep looking around to something you already know, and you find more information, and you keep refining and refining your knowledge and your designs. So in my continued fascination with the common emitter amplifier, I have found a much easier, simpler, and more intuitive way to calculate the components. Of course, you could just Google common emitter amplifier calculator, plug in some numbers, and there you go. But if that's all you wanted to do, you wouldn't be on this channel. So, common emitter amplifier made easy. Let's go. Here's our standard common emitter amplifier. This is the bias portion, and this is the amplifier portion. The input signal with its capacitor is here. The output signal with its capacitor is here. And you would have your capacitor in parallel across here. But we'll just worry about the amplifier part, because this is the important part. The capacitors are for the input and output stages of actually plugging in the audio. This is the amplifier itself, and you could put multiple stages of this and use it in different ways. So this is really the core and the mathy part. The capacitors, if you just recall, the video on that is the capacitor should be greater than or equal to 1 over 2 times pi times the frequency times the resistance. The frequency is the smallest frequency of the signal that you need to pass through, and the resistance is the resistance, impedance, whatever, of the input stage, output stage, whatever, that you're trying to put it through. So, for example, the capacitor here, you would use this in parallel with the load impedance. So however many ohms this is in parallel with, let's say, an 8 ohm speaker, calculate that output impedance, and that would be your capacitor. But it's just that. The same thing we went over before. But right now, we're going to do some easy math, and I'm going to label these. The positive I'm going to label as V amp, the amplifier power. If you have your set of speakers, this is the power it plugs into the wall with its little wallboard. The bias resistors will be R1 and R2. This will be RC for collector and RE for emitter, and then CBE is just collector base emitter. So it's super easy to do this. First, you choose your V amp. 5 volts, 9 volts, 12 volts, 24 volts, whatever. You decide what you have available to you, what kind of power you're probably going to need, and you pick the voltage you're going to have coming into this system. So let's say that's 9 volts. 9 volts. Then you pick your voltage of RE quiescent. This is the quiescent state. No input plugged in, no output plugged in. Now the output being plugged in only changes the impedance really, so we'll not worry about that too much. The input not being plugged in just means the signal is effectively always 0, because the input signal just pushes with or against the bias. So the bias is whatever voltage, and then if you have a positive signal, it'll add to that and increase the voltage from the bias, and if it's a negative signal, it will decrease the voltage from the bias. So a 0 signal or an unplugged signal are the same thing. So this is just always 0 signal. And we work with this because the signal will go up, the signal will go down, but it's centered on this point. So we want to do the centering based on that. And we've gone over this before. It should be 1 volt or 10% of the supply voltage, whichever is greater, is the rule of thumb usually. So 10% of 9 volts is 0.9 volts, so we just say 1 volt. If you had something like 24 volts, you'd probably want 2.5 volts or something. This is just a rule of thumb. Bigger is safer, but it's more wasteful and you lose gain. But you can make it bigger, just don't make it too small. Recall that the emitter resistor dampens the effect of power ripple, dampens the effect of changing beta on the transistor, so you need just wiggle room there. But RE, the voltage drop on RE goes up and down with the signal. Then if this is 1 volt, your signal goes minus 1 volt, it goes to 0. Now, you're probably not going to have a signal that goes all the way to minus 1 volt. So this is probably not going to go to 0 and you're safe. But if you think the signal might be stronger, then increase the voltage drop on RE to make sure that the signal never dips it down to 0, because if this goes to 0, then your signal pushing the bias down is going to start eating into the base to emitter voltage, and you're going to lose that forward bias and your transistor is going to turn off. But right now we'll just say 1 volt. So that's 9 volts, and at quiescence, this is going to be 1 volt. Then we decide on the base to emitter voltage. So voltage of base to emitter. This is just the standard approximation we use for diodes and transistor bases. We'll say 0.7 volts. Just a standard number. You can use it everywhere. It's good enough. If it's not exactly that, that's fine because RE gives you wiggle room. So these are just the things you decide on. Just go for rules of thumb. So if we look at the voltage across this whole thing, so from 0 volts here to V amp here, this chunk down here is VRE at any particular moment. Right now we're talking about quiescent, so let's say quiescent. Let's say we're at quiescent. So this is going to be your 1 volt-ish. So we get from here to the emitter. Now, from the emitter to the base, we get V base to emitter. That's your 0.7 volts, so now we're at the base. So now we have base to collector and RC. So basically this is our headroom. This is the amount of voltage room the transistor can go up and down in response to the current, because you have the base current determines the collector current, and the collector current by V equals I times R determines the voltage drop across this resistor. So at quiescent, we have this much room. Now, quiescent is the middle. We want to go up from the middle and down from the middle. Putting it in the middle of the room we have gives us the best available space so that it never bottoms out or shoots off the top. So we just do voltage of RC at quiescent equals V amp minus, and I'll go over all of this in summary at the end, just all the equations in a row. Right now I'm just going over it, so if you're having trouble keeping track, go for the summary at the end. But it's V amp minus, and one thing I didn't say is V bias, because we're setting this base, right, this resistor there, which I just erased. There we go. V bias, this is the bias we're applying, equals the resistor on the emitter at quiescence plus base to emitter. Basically, the voltage drop across this resistor has to equal where we want the voltage drop of both of these. So we bring it up across this resistor and up to the base. We want this to equal it because you can see it's on the same horizontal level. We want this point to be that point. So V bias equals V of R2, if we want to say it that way. So this is the bias voltage. But the quiescent collector voltage, we want this spot right here in the middle. It's the total voltage we have minus V bias, because the bias, this is the bias, it's taking away from the total voltage we have. So this minus this is this over 2. So we want this resistor to be dropping half of this and this transistor to be dropping half of this. So this here would be V of RC quiescent, and this would be the voltage trans whatever. So if we have 9 volts minus 1 volt minus 0.7 volts, we get 7.3 volts. So 3-ish volts here and 3-ish volts here. So the collector to emitter would have 3 some volts and this resistor would have 3 some volts. And then the signal going up and down will make this resistor have more or less, which will make this have less or more. So that's why we're putting it in the middle. So we can say V bias equals 1.7 volts. And then we can say V of RC at quiescent, which is half of our headroom. So 9 volts minus 1 volt minus 0.7 volts is 7.3. Half of that is 3.65. So 3.65 volts. Now you decide on your power. When the signal is at 0, how much power do you want going through this resistor? My resistors can take 0.25 watts, so let's just say 0.2. Let's say the power being dissipated by RC at quiescence equals 0.2 watts. That's how much we're just going to burn sitting there. Now the bias will be burning it too, but it'll be less power. It'll still be wasted power, but this is the big one. This resistor here is where all the power is going through, the major part of it. So let's say 0.2 watts for safety. We know that P equals V times I. So I through RC at quiescence equals, we just take the power target, divide by the voltage, so 0.2 divided by 3.65 equals about 55 milliamps. So at quiescent, we're going to be getting that much current through this thing. But we also know that V equals I times R. Well, the voltage again, and now we have the current. So if I take 3.65 volts divided by that amount of current, we get RC equals 67 ohms. Now that's pretty small. if your parts can handle this, then that's great. It has very low output impedance, not as low as it could be, but fairly low. But you're going to need good resistors, you're going to need good transistors. When I try this, it actually ends up heating up the transistor quite a bit. Now, they're rated for 650 milliwatts of power dissipation, and when I'm dissipating only 200 some milliwatts, they get warm. So I'm just trusting the spec. Perhaps them being that warm is perfectly fine, but be aware that they are getting warm. If you're worried about this, just increase this resistor. You're the one setting the power target, so if you want to change this to 0.1 watts or whatever, just increase this resistor. In fact, you could just pick a random number for this resistor and calculate from there. But now we actually know this resistor's value. So that's nice. So let's say it's about 67 ohms, and we said the current through RC at quiescence, the collector current, was about 55 milliamps. Now you pick your beta. So collector current is about 55 milliamps, and we're putting about 9 volts through it. If you go in your transistor datasheet and you see an entry called HFE, it's usually called HFE. I forget why, but it doesn't matter. That's your beta. And it's going to usually, if it's a good datasheet, give you different values based on the rough range of voltage through collector to emitter, so 9 volts, and collector current, so about 55 milliamps. So if I look on the datasheet for the 2N2222A that I'm going to use, it says that on the order of, and this was just one manufacturer, but the minimum range is around 10 milliamps, 30 milliamps, ends up being around 70-ish, 75, go up to 150 milliamps. This is with 10 volts. 150 milliamps ends up being 100, but those are minimums, and they go up to 300. So, lots of variance. But this just shows, if you go on the internet, you'll usually see 100. Like, pick beta is 100. 9 times out of 10, they're going to be approximating beta with 100. So I recommend you just don't worry about it too much and do that, unless you have a weird transistor. So we're going to pick beta equals 100. So this is the approximation we'll use. The current through the base at quiescence equals the current through the collector at quiescence over beta, because beta is known as the amplification factor, the gain, the current gain. So just divide whatever you got here by 100, so that'll be, on the order of 550 microamps. So now the current through RE at quiescent equals current at the base quiescent plus current to the collector at quiescent, because you've got the base current going through here and the collector current going through here. And V equals I times R, so divide the voltage of RE quiescent. So we just get our 1 volt, that's the voltage drop we want, this current, and we get, in this case, 1 volt divided by the collector current plus the collector current again, divided by beta, this right here, divided by 100. And we get about 18 ohms. Again, a pretty small value. 18 ohms. It's supposed to be an 8. Take my word for it. So all we've done is either figure out the current that goes through here and then use a power target to figure out the resistance, or we could just pick a resistance and then figure out the current from there. I like this way better. And then we can figure out the base current from the collector current, add them together for this current, and use the same thing, just Ohm's law. It's just Ohm's law, Ohm's law, Ohm's law. So that was easy. Then we have to figure out this. Recall where I said that we want this to be providing at minimum 10 times the base current we need at quiescence, and more is better. So basically this is a waste. It's always putting power through. But by having that headroom, and times 10 is just a rule of thumb, somewhat randomly, just more is better. But this helps with your stabilization of the emitter resistor to make sure it always can take or not take what it needs. So you just do the same thing. You have your base current, right? Multiply that by 10. There's the current you need. Then the total resistance, right? So you have R and you have I. So you just take your base current, right, times 10. So you have 10 times your base current. You have your V, your amplifier voltage from here to here, because it's in series, so they add together. V equals I times R. So R equals V divided by I. So V amp divided by the current through the base at quiescence times 10. And then this is giving you R1 plus R2. R2, the total resistance. And we want this to be greater than or equal to, or flip it, less than or equal to. We want the total resistance to be less than or equal to this voltage divided by this current. Less is fine, more is more dangerous. So we could write it the other way, if it's confusing to see it in that direction. R1 plus R2 less than or equal to V amp divided by 10 times the current through the base at quiescence, if that looks more clear to you. Same as it was before. So that gives us a total resistance. Well, we just decide what that is. Then how do we find the resistor values? Well, R2 equals R1 plus R2, right, the total resistance we have, times. Now we do a ratio. V equals I times R, Ohm's law. It's linear. Changing the resistance changes the voltage, changes the current, everything is linear. So essentially, whatever percentage of the total voltage this resistor should have, it's the same percentage of resistance, of the total resistance. So if this wants to be 30% of V amp, then it's 30% of the resistance. So voltage of R2 over voltage of R1 plus voltage of R2, just to make it clear, see? But that's just V amp. V amp. V of R2 over V amp is the factor, the percentage essentially. If you multiplied it by 100, you could say percent. It's how much of V amp VR2 is carrying. And you just multiply that factor, that percentage, into the resistance, because it's the same thing. 30% resistance, 30% voltage, same thing. And it's the same the other way. R1, R1. The percentage of V amp that R1 is carrying is the percentage times the total resistance is its resistance. So that gives you the other two resistors. So let's do that. So if I have my collector current divided by 100, gives me my base current, which is about 548 microamps, times 10. All right, so we want to make sure we have at least 5.4 milliamps going through there. V equals I times R, so V divided by I equals R. So if we take 9 volts divided by that current, we get about 1642 ohms. So this is the total resistance that we want, or less, right? Less than or equal to. So we could have 1642 or we could have less. So whenever you're picking your resistors out of your box, just pick the next lowest. So V bias, which is what we want on this resistor, 1.7 divided by 9. So that's VR2 divided by V amp. So this resistor is carrying about 18.9% of the voltage, which means it wants about 18.9% of the total resistance. So that times our 1642, and I get about 310. So we say about 310 ohms or less there. And then the same thing up here. So if I have 9 volts minus 1.7, 7.3 volts is what's going over here. Divide by 9. So about 81% of the voltage of this is over R1. So about 81% of the resistance. So 0.81 times 1642 again, and I'm just scrolling up to the exact results in my calculator, is about 1332 ohms, less than or equal to. Now that took forever, you will say. I thought this was supposed to be easier. Well, the part that's different was basically the voltage calculation. Because before they picked a resistor and then they picked the current based on that and took half the current and went from there. This makes more sense. Because you're basing the current on your power target and you're basing your resistance on that. You're actually saying, this is how much voltage headroom I have. I want to get in the middle of that voltage. How much current gets me in the middle of that voltage? It follows more along the lines of a BJT is modeled as a current-controlled device. So we're more directly saying we get a voltage on the collector based on the current through the collector based on the current to the base. So I just think it makes more sense that way. You know that little bar chart I made? It's more in line with what we're actually doing. So now I'm going to very quickly go over this again, and I'm just going to put the math you need to do. So now that you understand it, now I'm going to give you what to write on your paper so that you end up doing this. Quickly and easily, anytime you want to make one of these, it'll be nice and easy. So once again, you choose your V amp. Whatever power you have or want to supply, just pick the nearest available wall wart, or if you're going to buy one, just decide, 9 volts, it's not a very big speaker, maybe I could get away with 5 volts. Or you're trying to drive a big ol' subwoofer or something, you're going to want maybe 12 or even 24. You've got to have some power through there, which means you need big transistors and resistors as well. This is why there are Class B and AB amplifiers amplifiers because they use a whole lot less power. They have much better power efficiency. But Class A, which is this, has the best quality. There is no better quality amplifier than a Class A because the entire signal goes from input to output unmolested, complete replication at the cost of extreme power. So if you don't care about the power usage, buy really strong resistors and transistors and do it this way. You'll get the best quality. Even better, if you can leave off the capacitor here, you'll get even less gain, but less distortion. So, multi-stage with power transistors, and there you go. So you pick your V amp. You pick your V across RE at quiescence, 1 volt or 10% of the supply voltage, whichever is more. If you have a high voltage signal, then it needs to be higher. If you're dealing with audio, usually it's 1 volt peak to peak, so 1 volt minimum is fine. More is better, but diminishing returns because it cuts your gain. So I would just go with the 1 volt or 10%. It'll be fine. And then you pick your voltage from base to emitter, which is just the forward voltage drop of this junction, 0.7. Just go with 0.7. So then you calculate V bias equals the voltage across the emitter resistor at quiescent plus voltage across the base to emitter. So if you have 1 volt and 0.7 volts, it's 1.7. That is this total voltage drop here, which is going to be across R2. Voltage across the collector resistor at quiescent equals V amp minus V bias. That's the leftover voltage over 2, and that puts it in the middle. So the transistor has half and that has half. The current through the collector at quiescent equals, you decide how much power through the collector resistor at quiescent. So you decide on your power supply, you decide on the emitter voltage at quiescent, the base to emitter junction, and the power dissipated by your resistor at most, because this resistor is supplying the transistor and your load. So once you have that, current through the collector at quiescence equals your power through the collector resistor at quiescence divided by the voltage through the collector resistor at quiescence. So now you have your current. So that means your collector resistor equals, once again, voltage across it, quiescent, divided by the current across it. Because the current going into the collector is the current going across this resistor at quiescent. If you connect a load, some of the current is going through there instead, but the total will remain the same. So this is just P equals V times I, Joule's law for electronics. This is just Ohm's law, V equals I times R. So now we have RC. We have the collector current, so the base current at quiescent equals collector current at quiescent divided by beta. So we also decide on our beta. I recommend just saying beta is 100. You can look at your data sheet for the transistor you're using and see if it's going to be some weird number, but 100 will work. It'll get you in there. Everything in electronics is a window. Nothing's going to be perfect. So now we have the base current. The emitter current at quiescent equals the collector current at quiescent plus the base current at quiescent. Emitter current is just base current plus collector current, which means RE equals the voltage, so voltage of RE at quiescent over the current of E at quiescent. Once again, just Ohm's law, V equals I times R. So now we have RC and RE, and I've run out of space. But don't worry, we're almost done. So the current through the bias, the current through this must be greater than or equal to 10 times the current through the base at quiescence. It can be more, don't make it less. 10 is a nice even number. It's pretty. So the resistance, 1 plus R2, must be less than or equal to the voltage, once again, Ohm's law. It's just Ohm's law. V amp over 10 times IB at Q. V equals I times R. So you get that total resistance that you want to work with. R2 equals R1 plus R2, the total resistance, remember the percentage. So the percentage of the resistance is the percentage of the voltage, times V bias over V amp. The percentage of the bias, because this is V bias, of the total V amp times the total resistance. And R1, I should say less than or equal to, so you can pick a smaller one. R1, which is that one, is less than or equal to R1 plus R2 times V amp minus V bias over V amp. So this is V bias, this is what's left over after V bias, and it's just the other percentage. And that gives you your R1 and your R2. And that's it. You decide on your voltage you have from your wall. You decide on your voltage across RE at quiescent, your safety margin. Decide on the 0.7 volts here. Then you calculate how much voltage can go over here, which is the total but a half. You use a power target, decide how much power you want running through here when there's no signal or the signal is silent. Calculate a current from that power and this voltage. Calculate the resistance from that current and this voltage. Use your beta that you decide is probably 100 to calculate the base current from the collector current. Use the combined current with the voltage here at quiescent to decide on this resistor. 10 times the base current is this total resistance, so you decide on that total resistance or less. Then you just use the percentage, V bias, and the rest from V bias to get your two resistor values, and round down when you look at your box. That's it. That's all the steps. You calculate a voltage, then you calculate a current, then you calculate a resistance, then you calculate the other current, add them together to calculate this resistance, then you have that current, you calculate a resistance, then you split it up based on voltage to get you two resistances. The entire thing, almost the entire thing, is just Ohm's law applied a whole bunch of times. It really is simple. So this makes how many common emitter amplifier videos now? I just really like this circuit, and I hope you do too. But that's all for now, so I'll be seeing you